Thank you. Hello, everyone, and welcome to my talk on transforming noise into insight through automation. A little bit about me. My name is Anicet Fopa Tchoffo. I currently work as a security consultant at the University of Leeds. I'm also a researcher and am passionate about automated investigations. Some of what I'm going to discuss today includes a fraction of features usually found on expensive EDR dashboards, but I'll talk about how to replicate them using free or open source tools, especially for those with limited security budget. So what are we aiming to achieve here? In a traditional SIEM setup, your endpoints and network devices send their logs to your SIEM, where the detection engine evaluates those logs and generates alerts as needed. At this point, an analyst has to review those alerts, correlate the data, and perform investigations. What we're going to do, we're going to introduce a tool that will automatically pick up those alerts, extract relevant information, run correlated searches, summarize the findings into a report, and store that report into a different index. So I've been working on a tool called Kibal Core, and when I started working on it, I was a one-person army doing the job of 5. And I wanted to automate some of the correlation tasks during investigations. I also wanted to automatically detect and deobfuscate obfuscated PowerShell. And ultimately, I wanted to streamline the process of adding context to an alert to speed up the identification and scoping process. For this, I used an Elastic SIEM with a basic license. I leveraged Windows native event logs as well as Sysmon logs. Quick reminder on Sysmon. Sysmon, it's an agent that you can install on your endpoints that will record several actions performed by a process on that system. When a new process is created, Sysmon automatically generates a globally unique identifier and assigns it to that process. It also records information about the user that started that process as well as the parent process, if there is one. Subsequently, when that process performs other actions on your system, Sysmon will record a relevant event. And to tie those events back to the original process create event, Sysmon will copy that process GUID to the subsequent event. Currently, from an event perspective, Sysmon can create events when a process performs any of the actions listed here. Here are the event IDs. The ones highlighted in red are the ones that do not have a process GUID because they're not tied to a specific process. So let's say we are alerted by, an alert is triggered by a DNS event, for example. I don't know, maybe someone accessed the domain that was registered less than 2 months ago. By using the process GUID on the event as our reference point, we can find out all the actions taken by that process on the system. Next, if we find out the GUID of the parent, we can use that as our new reference point. We can find out all the actions taken by the parent on the system. By using the same logic, we can find out what the parent of the parent was, which I call ancestor 1 to start with, because otherwise the lineage becomes very complicated. So I just call it ancestor 1, and as we go up the chain, I just increment the number as we go up. If you come back to the original process, we can find out all the GUID of its children, and if we use that as reference for correlation, we can find out we can do the same thing going down. So now when we are alerted on an action taken by a process on the system, we can automatically put some context around it and establish where did it come from and where did it go. If we can find out the user name and the logon ID, we can query built-in Windows event logs to find out other actions taken by that user this time on that system. Things like, how did they get onto that system? Was it a hands-on keyboard logon? Was it network logon? Was it RDP? What was the source IP? And so on. There are many techniques that can be used to elevate your privileges on a Windows system, and some are stealthier than others. So depending on what technique was used to obtain admin access, there might be an event log that was logged to reflect that. Things like special privileges assigned to a new logon, the existence of a linked logon ID, and so on. We can also pull up all notable actions, security-related actions taken by that user on that system. Things like user and group management, schedule task management, service management, event log cleared, and so on. We can also add HR information. Now, for this, it requires either you synchronizing some of your HR information into an index into your SIEM, or if your HR system offers an API that can be leveraged, the tool can do that. And some of the information that we can add here includes the user status. Are they still employed with us? Their department or unit? And in this case, let's say you see somebody running PowerShell. If they're a sysadmin, maybe that's okay. But if they're from marketing, that's probably something you need to take seriously right away. We can add their contacts, their location, their manager, so that if you need to reach out to someone, that information is right there. Quite often, during investigation, you come across things like this. base64 encoding in the process command line. And attackers and red teamers will do this to hide what they are doing. And what you typically have to do at this point is identify and extract the base64 yourself, move away from your SIEM into a different tool to try and decode it. And plus, they will use multiple layers of obfuscation to make your job as an investigator more difficult and challenging. And it typically looks like this. They take a payload, do something to it, do something else to it, and then do something else to it. And they will throw all kinds of things in there. Unicode, binary, XOR, compression, encryption. There are so many possibilities. And to reverse it, you have to do the exact same thing, but in reverse. So typically, the easiest things to do is decode the base64, but you often end up with some more garbage. Now you have to work out what that garbage is so that you can reverse it. And again, there are tools out there that will allow you to do this, but they require you taking the information out of your SIEM into one tool, and sometimes you have to move to another tool, depending on what you're dealing with. So, what KibalCore would do in this case is whenever it detects base64 in the process command line, it automatically extracts it, decode the base64, try to determine the next step, so the data type that it got after the base64 decode, reverse it, and keep doing it until it gets to something it can no longer deal with. And as it goes through that process, every time it detects a data type, when it reverses it, it records what it did just to give you that full context directly within your SIEM, so you can understand sometimes when you have to make the call, as in, is this benign, is it not, based on all the different type of encoding and obfuscation steps taken, it can allow you to make that call quickly. Quite often when deobfuscated PowerShell, you end up with plain ASCII, but you still can't understand what they're trying to do, because they would they would use aliases, shorthanded versions of commands, string-based manipulation techniques, and in this case, we can use the PowerShell abstract syntax tree to revert some of that stuff. So, Kibalcore is written in Python and PowerShell and can run as a Linux service, a cron job, or ad hoc. And when events are sent into Elastic, Kibana creates an alert. Kibalcore will automatically pick up those alerts, perform correlation, and store the report. The detection engine in Elastic is called Kibana. So, and the tool name is short for Kibana Alert Correlator. So we're going to move into demo. To demo the features of the tool, I used publicly available malware data from the Splunk Attack Range project. So kudos to them. In the demo setup, I have a deployment of the Elastic, a deployment of Kibalcore. I also use the Hive Community Edition to facilitate the navigation between datasets. So, to avoid issues related to live demos, I pre-recorded a video of a typical Kibalcore report, which I'm going to play now. Bear with me. Now, there's a lot going on the video, but I added some arrows to help, keep track of what's going on and what I'm talking about.
Here we have an alert that was triggered because someone ran a command that says, show me all domain user accounts. Now, is this a sysadmin? Is this common in your environment? Maybe you've seen this before and it was fine. How do you know this time it's not? The severity here says low, so if you're receiving more alerts than you have time to investigate, this is probably something you wouldn't prioritize at this time because you would be working on your higher severity alerts. So let's check out the correlated report that was generated to see what additional context was added for this alert. The report is easier to read in JSON format, so let's switch to the JSON view. The first section contains information about the environment and the rule that was triggered, so let's skip it and fast forward to the interesting part. Here we are looking at the process lineage that was generated. It starts with ancestor number 8, which was explorer.exe, so we know the user probably had graphical access to the system. Explorer.exe had 20 children, and we have summary information about them, including their unique identifiers. These children include cmd.exe, PowerShell, 7-zip, and so on. Explorer was observed making network connections, creating files, setting registry values, creating and connecting to named pipes, and deleting files. The network connections were directed to a public IP address that starts with 51 and ends with 159. And socket information shows that these connections were made on port 443. We also have the list of link files created by Explorer, indicating the files or directories that the user may have accessed. Next in the lineage is ancestor number 7, which is cmd.exe or Windows Command Processor. And if we pay attention to the process command line, we see that the user started cmd and changed directory to the downloads folder. CMD had one child process, run_dll32. Therefore, the next ancestor, number 6, is run_dll32, which is a process that enables Windows to execute functions stored in DLL files. Here, the command line reveals that run_dll32 was invoked to run the function *w within the DLL file named 1.dll. Given that we previously changed directory to the downloads folder, we can infer that this DLL file is located there. So during the next phase of our investigation, we should attempt to obtain a sample of this DLL file, provided that it hasn't been deleted yet. Run_dll32 had one child process, also run_dll32, but this instance was located in the syswow64 folder, which on 64-bit systems is the 32-bit version of run_dll32. This indicates that the DLL named 1.dll is a 32-bit DLL. So next, ancestor 5 is 32-bit run_dll32 with the same command line arguments as before. It had one child, warmgr.exe. Next, ancestor 4 is warmgr, which is the Windows error reporting process. It had 8 children, 7 of them being instances of cmd.exe, and 1 of them being a process located in the user stamp folder. This Windows error reporting process was observed performing network connections, accessing other processes, creating files, and performing DNS queries. The network connections were directed to 4 public IP addresses. And socket information reveals connections to the IP starting with 95 were made on port 80, to the IP starting with 67 on port 443, to the IP starting with 98 on port 447, and to the IP starting with 104 on port 443. It accessed the LSOS process and created 2 files, one of them in the temp directory and another one in a subdirectory of the rooming directory. These were potentially downloaded through the above network connections. We have all the DNS queries performed here. Some yielded responses, while others did not. We previously observed network connections to a public IP starting with 104, and now we know which DNS query resolved to that IP. Similarly, for the connection to the IP address starting with 95, we have identified the corresponding DNS query. Next, ancestor number 3 was an instance of cmd.exe, and here's what its command line arguments looked like. It called PowerShell and passed it what looks like a base64 encoded string. This CMD process had one child, PowerShell. Because base64 was detected in the command line, it was automatically extracted. It then went through the deobfuscation process, and here's what the result looks like. Even if we're not PowerShell experts, we can still look for keywords that will give us an indication of what the code is trying to do. For instance, the function IOMemoryStream is commonly used to download and execute code directly in memory without writing to the file system, a technique often employed by fileless malware. Additionally, the presence of a byte array, typically used to store and execute malicious payloads in binary format directly from memory, is another indicator of potential malicious activity. Here are the steps that were recorded during the deobfuscation process. We decoded the base64 data, revealing some bytes. These bytes were further decoded, during which Unicode null bytes were identified and cleaned up. We then analyzed it using the PowerShell abstract syntax tree. This process outlines how the code was obfuscated. If you need to decode it again, just follow these steps. Now we go down to ancestor number 2, which was PowerShell, and we see all the command line arguments passed from cmd.exe with the same base64 encoded string as before. This PowerShell process had 8 children, including run_dll32, CMD, and PowerShell itself. It was seen performing network connections, creating files, creating and connecting to named pipes, performing DNS queries, and deleting files. Because base64 was passed to CMD, which then passed it to PowerShell, it means it was detected and deobfuscated each time. So this next deobfuscation block is similar to the previous one, so let's skip it. The network connections were directed to a public IP address starting with 23 and ending with 84. Socket information shows these connections were made on port 80. We have the named pipe that was created by this process and the ones that were accessed. Their names start with the prefix postx. Named pipes with the prefix postx are typically associated with post-exploitation activities in malware or attack frameworks. Next, Ancestor1 was another instance of cmd.exe. We see the command line arguments were net user's domain. It had one child, the net command. So naturally, that's going to be our parent in the process lineage, and the command line arguments are the ones passed from CMD. It had one child, the net1 command. If we look at the command line argument, we see that this is what triggered our alert. So now, based on the additional information provided by the report, we not only know that something malicious is going on, but we've also gathered numerous indicators of compromise such as domain names, IP addresses, file locations, and these would be crucial for the next phase of our investigation, which is scoping.
So we've demonstrated how we can take an alert that most analysts can ignore if they are, overwhelmed with, hundreds of alerts to deal with. And we show how with the context added by the tool, it basically, to assess this, it's basically how long it will take you to read the report to, determine that something malicious is going on. Also, it's done a lot of the pre-correlation and investigation for you. So you have, you now have IOCs that you can start using to either block stuff on your firewall or scope and see what other system may have been affected and things like that. So, and that's why the tool is so valuable. Questions?
Can we get it?
I'm still working on some features, ideas, and I'll publish it at some point. Just watch out for it.
Does Sysmon has any temper protection? What if the virus itself disables Sysmon first?
As of Sysmon version 15, it now runs as a protected process, as same as your EDR product. So prior to version 15, it was fairly easy to disable Sysmon on your system, but it now runs as a protected process as of version 15.
Does that give you a hash at every step of the attempted deobfuscation of the PowerShell scripts? That give you a hash for each one.
What do you mean by hash?
So it was hash, SHA, and MD5, just for integrity.
Yeah, I mean, the SHA and MD5 are taken from the signature of the process. And now, in this case, everything within that chain were built-in Windows processes. That's why I didn't emphasize on the hashes, because those are built-in Windows processes to begin with. But when you are dealing with processes that they brought in or that they compiled on the fly and things like that, that's where it will tell you the hashes, and that's when it can also be used to further scope. Yeah.
One more question. Running up to time, so this is one more question you want to...
said,
Go.
can we use Splunk instead of
Now, it will work with most SIEM that have a JSON, backend. The issue with Splunk is Splunk store different data set in different format, and having to accommodate all those formats is pretty complicated. It was much easier with Elastic because everything is JSON, so I know exactly the format of what I'm going to get. So it's easier to parse and create a report of it. So that's the only challenge with Splunk. I tried Splunk, but it was just very challenging. Yeah.
If you've got any more questions for Anicet, find him outside. I'm sure he can talk for a long time about this. It's an amazing product. It is cool.
Yeah.
Feel free to ask him.
Yeah.